Welcome to lecture 24. In lecture 24, we're going to work the POGL activities 11B. Okay, so model 1, we are doing the addition of water, alkene, hydration. We're going to add HOH, okay, to the double bond. And I'm actually going to do it like this, HOH, because OH will add to one of the carbons and hydrogen will add to the other carbon, and that's water. In model 1 we have this, and you see one of these we do sulfuric acid and water. One of these we do mercury acetate, water, and then the second is sodium borohydride. And the third one we do BH3, hydrogen peroxide, and OH minus. And then our products here, OH, OH, and we see that we have stereochemistry here, so that should tell you when you're learning your reactions that's going to be stereo specific. Okay, so question 1A. Compare the products of the 3 hydration reactions shown in model 1. What functional group is formed on hydration of an alkene? So what's the functional group here? Did you say alcohol? Okay, 1B. Which reactions in model 1 affords products that have the same regio chemistry of addition? What does regio chemistry mean? It means that the OH is added to the same carbon of the carbon-carbon double bond. So you got this carbon and this carbon here. So the red carbon, we have the OH, and that means the blue carbon got a hydrogen. Okay, so did you write sulfuric acid and water, and mercury acetate, water, sodium borohydride? Okay, question number 2. For each reaction, determine if the hydrogen adds to the least or the most substituted carbon of the alkene. Label each product as model. For model 1 is Markovnikov or anti-Markovnikov. Okay, so this means that the hydrogen added here, if the OH added here. So if the hydrogen added to this carbon, it's disubstituted, and this carbon is trisubstituted. So this added in a Markovnikov fashion. And I like to make my intermediate here. So if you do the intermediate here, you add your hydrogen here, then you add a carbocation over here. And you see that this is more stable. This one also was Markovnikov. And then this would mean this one's anti-Markovnikov. Now, if I were you, I would make a reagent sheet, a reactant sheet for each one of these reactions. So that would be 3. Okay. Indicate whether each reaction 1 occurs as syn addition, anti, or if it cannot be determined. Okay, so the only one that has any stereochemistry, as you see with the wedges and the dashes, is the last reaction, which is hydroboration, oxidation, and you see that the hydrogen and the OH add on the same phase, so that would be syn addition. Okay, so that's the same side. All right, let's go to Model 2. Model 2 is called acid catalyzed hydration. So this is the first reaction that we just saw. And we're going to talk about the reaction mechanism. You have to know each one of these reaction mechanisms. And here the acid. We mostly use sulfuric acid as your typical acid, but you could have other acid. And we have our product here. Now, question 4A. In the reaction shown in Model 2, which reagents are reacted with the alkene? Okay, so the first one is H plus and water. So you're going to see the H plus is here. This is where your acid goes. And then the OH from water adds here. H plus acts as a what? Did you write acid? Did you circle acid? Recall the Lewis acid-base definition. An acid will accept electrons. So it's going to accept those electrons, and the alkene will most likely donate electrons. Okay, so your nucleophile, you have your double bond there, and that's going to donate the electrons. So 5, consider the mechanism for the addition of HX as shown below. Label each reagent as nucleophile, electrophile, acid, or base for both steps. Okay, so this was from our first POGL activity earlier, and you should already know this mechanism. Well, this is your nucleophile. I want you to label that. And then those electrons add the hydrogen. So here's your hydrogen that gets added. You get your carbocation. This is step 1. We have 2 electron flow arrows. Now the chloride is over here. And in step 2, the chloride adds to the carbocation. And this was your mechanism. So this is your electrophile. And then in this step, this is your electrophile, and this is your nucleophile. They kind of trade places. So from the mechanism above, what is the first thing that happens when an alkene is combined with an acid? Did you write that the acid, the H plus, adds to the carbon-carbon double bond? And it adds to the least substituted carbon. So that's the Regio Chemistry. Of course, you can't really tell there. To generate your most stable carbocation. The curved arrow showing the formation of the carbon-hydrogen bond bounces off one of the carbons of the double bond. What does this mean? The way they drew it is they're showing you that the electrons both go to form a new CH bond. Okay, so for number 6. Question number 6. The mechanism for hydration is similar to the mechanism for HCl addition shown in 5A above. Draw the cation obtained from the reaction of the alkene with the acid above. So what you would do here, and so I don't redraw it, I'm going to just do it here, okay? And then the carbocation that you would draw in your notes, the hydrogen adds here, and then you get a carbocation on the more stable tertiary carbocation. This is tertiary carbocation. Whoa. Okay, page 135. The proton should add to the, so it added to the, did you circle least substituted carbon of the alkene? In the second step, the cation will act as a electrophile. Consider the reagents present in the acid catalyzed hydration. So you have alkene, you have acid, and you have water. Which reagent is most likely to react with the intermediate carbocation? The water, right? Because the water has lone pairs. We're talking about the carbocation here. Which reagent is most likely to act as this reagent is most likely to act as a nucleophile because it has the lone pairs. Did you circle nucleophile? Draw the mechanism for the second step above showing curved arrows. Remember that the reaction is conducted in water, not hydroxide. Okay, so the next step here is water. We do this reaction in water, and water will, its electrons will go to the carbocation, and you will form, put the hydrogen in here. Okay, and then what you have to do basically is the water would do a deprotonation to give you your final product, which would be, it regenerates your acid. And the acid is catalyzed. So this would be OH, your hydrogen would be there, and then that would generate H3O plus, which is your acid catalyzed. Is the product in the second step the same as the final product? No. If not, what's the remaining step that must occur to obtain the final product? And that's deprotonation. Okay, 7. Once your group has reached consensus, discuss what the product might be in a reaction of the alkene done in methanol. So for number 7, if you did this reaction, an acid catalyzed methanol. Okay, so the first thing that would happen is the nucleophile, which is your alkene, would get protonated, and you would form the carbocation. And this would be your carbocation, which would be a tertiary, so it'd be more stable. So the hydrogen would add to the least substituted carbon. And then your nucleophile here, so now this is your electrophile, and this is your new nucleophile for step 2. Would come in and add there. And now instead of getting alcohol, you're going to get a different functional group. And what would that functional group be? And then you'd have to do a deprotonation step. CH3. This is an ether functional group. So if you do these in alcohols, you can get a different product other than alcohol. Okay, for model 3. Okay, model 3 is the second reaction, and it's actually, and you want to get another reaction sheet. This is oxymercuration, demercuration, and we have our methylcyclopentene. The first reagent, we're adding mercury acetate. It's showing you acetate here is this molecule here. So mercury, basically, this is what mercury acetate looks like. Mercury is big, and now I'll show you. So mercury acetate. Mercury will form 2 of these. Okay, and then you make an intermediate called the merconium ion. And then so one of the acetates falls off. This is called the mercurium ion. So anytime you have the inium ion, it's always going to be a positive 3-membered ring. You're going to see this. Intermediate. And you'll see this over and over. And then we add water. And water is going to add to this intermediate. This is kind of like a protected carbocation. And now water is here. And then the second step, this is step 1. The second step you have to add is sodium borohydride. So you'd let this reaction go for a while, and then you would come in and add your sodium borohydride, which is a reducing agent. Sodium borohydride has a hydrogen. It's a hydride, okay? And it will just exchange mercury for an H. In fact, I'm going to show you that Lewis structure here. Boron usually likes 3, so this gives us a negative. There's sodium borohydride, and this actually delivers an H minus. Okay, so that's a hydride. And that hydride is a reducing agent and will replace, so the mechanism there is the H replaces the mercury, the metal. So you got to have it. Okay, so that is model 3, and we're going to work through this reaction mechanism. Question number 8. The reagent mercury acetate can be viewed as dissociated into mercury OAC and minus OAC. Of these 2 species, which would most likely add to the alkene? That would be the plus mercury acetate, because your alkene is negative. Well, I mean, it has electrons, pi bond. Okay, 9A. Instead of forming a carbocation, a more stable merconium ion is formed. Okay, if one of the carbon-mercury bonds of the 3-membered ring start to break, the carbon more likely to hold the positive charge would be what? The most or the least? So whenever you get these merconium 3-membered rings and you have a full plus charge, then you've got to look at where would your delta positive be. And it's going to be at the more substituted, so the most substituted carbon. So it says plus, put a delta positive on that carbon. So that's what we did. The merconium ion intermediate will react with one of 2 nucleophiles present in the reaction. Okay, so there's the acetate here, and this is not nucleophilic. Okay, so when you have to decide between the acetate, which has a negative charge, or the water as your nucleophile in your second step, the water is going to be your nucleophile. And the reason why is these electrons on acetate are not really available due to resonance. So your nucleophilic electrons are going to come from the water. So you can circle water for B. All right, is the reagent circled the better nucleophile? Yes. If not, explain why it was chosen as the nucleophile. So also there's more water present than the acetate. Okay, so number 10, the question is, the last step in Model 3 is called demercuration. Okay, what bond is being broken and what bond is being formed? So the carbon mercury acetate is being broken, and then a carbon hydrogen bond is being formed. And that is showing you that right here. So this carbon mercury bond is being broken, and then the carbon hydrogen bond is being formed. This is called demercuration. Once your group has reached consensus on the above questions, discuss what product would result if the reaction in Model 3 was conducted in methanol. All right, so let's do this reaction, and you need to have this in your reaction sheet as well. And so if you used, first step, mercury acetate, and you did this in methanol solvent instead of water, and then the second step is sodium borohydride, which is your demercuration step. So once again, you can just write this as mercury O acetate positive, and your electrons go here, and you form a carbocation. Well, sort of. The merconium. So that mercurinium ion. And you want to put in your delta positive here, because that's going to direct your nucleophile in the second step. So now you have the methanol nucleophile that's going to come in to that partial positive and open up the mercury acetate. So you're going to break that three-membered ring, and now you're going to get OCH3 here, and then this is going to be mercury acetate. And then the second step is the sodium borohydride. This is just demercuration. You're going to replace the mercury with a hydrogen. So you can just take it off. You don't even have to put the hydrogen there. And so that would be your product from the alcohol. And that reaction is actually called alkoxymercuration. So alkoxymercuration. And it makes ethers. That's an ether instead of an alcohol. Okay, we're on Model 4, hydroboration. So now we're on Model 4, hydroboration. This was that third reaction, and we need to know that mechanism. And here we have a different substrate. And I like the way this is drawn, this reagent, sort of. It's really planar, so I don't put dashes and wedges for planar. So I'm not going to put a dash and wedge in there. And what you have here is, let's go ahead and put these as CH3, CH3. You have CH3, hydrogen, CH3, BH2, H and H. Okay, so you can make this a BH, and then this is your H. And I'm just going to go ahead and do that. Sometimes what I do when I'm first teaching this is I will draw this reagent as HBH2, just like I do with water, H and OH. So you know the OH is going to go to one of the carbons of the carbon-carbon double bond, and then the H goes to the other. Same thing with here. One of these carbons is going to get a H and the other one gets a BH2. So questions number 12. How many valence electrons does boron have? Well, what group is boron? Boron is in group 3, but it's given 1, 2, 3, 4, 5, 6. So it's sharing, so it has 6 valence electrons. The electronegativity value for hydrogen is a 2.3, and for boron, it's 2.1. So which one's more positive? Yeah, it's a boron. So you could actually put in your dipole such as that. Okay, so the more electronegative is hydrogen. Draw arrows for the structure for BH3 above to show the dipole. D. Which atom, BH3, is more likely to act as the electrophile? The boron, isn't it? Yeah, because the boron's more delta positive. Okay, in the mechanism for hydroboration, the boron and hydrogen add to the alkene at the same time. What do we call that? It's concerted. So this is concerted mechanism. Although a full carbocation is not formed, the transition state shows that the partial positive charge develops on the carbon that is not bonded to the electrophile boron. Okay, so that shows you that in your slide. Why does the addition occur to give Regio Chemistry shown above? The way I've always done this is more of sterics. I think of it sterically driven. So let's look at this here, CH3. Well, so on this carbon, it is going to get the hydrogen, and then the other carbon here is going to get the BH2, and since they add at the same time, they're going to be added on the same side. So usually you can even show that with maybe both making them wedges, or you can make both of them dashes. And if the boron is more delta positive, it can go to this less one that would be less substituted. I always think of more of boron is going to go to the less steric face, or the less sterically hindered carbon. This is syn because it's adding to the same side, so that's why I showed both wedges. So hydroboration is stereospecific, so you'll want to write that in your reaction sheet. During the first step, the boron and hydrogen are added at the same time to the double bond. Would you expect the addition to occur from the top face, the bottom face, or equally? And they're going to go equally. Okay, they're going to go equally top and bottom. So if you look at 14, so we have a reaction here, and the first thing we're adding is boron. And if you want to, you can just do it like this. So the BH3, you can split that up. And then the second thing is hydrogen peroxide, and that would be in a basic solution of sodium hydroxide and water. and it's showing you both reactions here. So you're going to get the hydrogen's going to add there to the less substituted, and then the BH2 would add here, but then it gets replaced with the OH. So hydrogen peroxide looks like this, and it basically replaces the BH2. And then they're showing you that it can come in from the opposite phase, where the CH3 goes down, hydrogen's going to go on the top, and then your OH, which was really your BH2, is also on that same phase. Label the products as Markovnikov or anti-Markovnikov because you're adding the OH to the less substituted carbon of the carbon-carbon bond. They call this the anti-Markovnikov. Okay, so it goes anti-Markovnikov because it's least substituted. Would you expect the products above to be formed in different or equal amounts? They would be formed probably in equal amounts. Okay, number C. Compare the hydration of alkene using hydroboration versus acid and water. So let's do this reaction here. And they're saying compare with BH3 and hydrogen peroxide, or the other one, which is hydroboration versus acid and water. So sulfuric acid and water. Okay, so the first one, and the first step, step 1, would put the, and you don't have to show both of them like we did earlier. You could just pick this here, and then you say, okay, the hydrogen would go here. I would want you to show at least one with stereochemistry. And then over here, the first thing that's going to happen is you're going to form a carbocation. It'll be there. The hydrogen's going to add to the least substituted. So, and then you're going to get the water coming in, right? And so you're not going to have any stereochemistry there because it's flat in the step 2. So there you go. You don't show any stereochemistry. You would show none. Here you would show both dashes. You could do both, or you could just do both wedges. So this is, the problem with this could have rearrangements. This happens to be the tertiary carbocation. This you're going to have no rearrangements, and you're going to get the Markovnikov here, and this is going to be the anti-Markovnikov with the hydroboration oxidation reaction. Okay, so 15. In your groups, compare the 3 different methods for hydration of alkene. Discuss reasons why one method would be preferred over the other. Okay, so let's do all 3 of them. Acid, catalyzed, and that reagent is sulfuric acid and water. The other one was oxymercuration. That's with mercury acetate and water. And then you have to do a second step, demercuration, and that is sodium borohydride, and that replaces the mercury. And then the other reaction is the hydroboration, because you're putting hydrogen and then BH2 boration across that double bond, and then you have to do oxidation. And so you do that with an oxidizing agent such as hydrogen peroxide, and that will be in a basic solution. All right, so those are the reagents that they're asking to compare. The Regio Chemistry, for the first one, acid catalyzed, is going to be Markovnikov. with possible rearrangements. Okay, because you got to have the carbocation and do the carbocation test. So you got to do the carbocation test. So you could have possible rearrangements. Regio Chemistry for oxymercuration is Markovnikov, and you have no rearrangements because that mercurinium ion will lock in that delta positive on the more substituted carbon, and that will direct your nucleophile. And then the hydroboration is anti-mark, so that means the BH2 is going to go to your least substituted, and then that's going to get replaced with hydrogen peroxide, okay, to make your water. This is also going to have stereochemistry, so you got to show dashes and wedges, and you'll show that with syn addition. Okay, and you will not have any rearrangements there. Okay, so for your additional problems, I need you to do 16A and C. Okay, you can omit B. Okay, so I need you to do A, C, D, and F. You can omit B and E. Okay, so you don't have to do B and E on number 16. And then 17, I need you to do the mechanism for each one of those, and you have A and B. So you need to show the mechanism. And you're required to know the mechanism on all of these reactions. And that'll be it for 11B.